For a century, internal combustion was a rigid binary. Engines use a spark plug or rely on compression alone to trigger a spontaneous explosion. This mechanical divide has created a century-long bottleneck. In practical applications, the standard steel engine loses most of its fuel energy to the environment, reaching a thermal efficiency limit of only 35 to 37%. Pure thermodynamics suggests we should be doing better. Mathematical models based on standard-specific heat ratios place the theoretical efficiency of these cycles much higher, at approximately 46%. That 9% discrepancy is the cost of operating in the real world. Energy that should be turning the crankshaft is instead conducted into cooling jackets, wasted during long burn times, or dumped through exhaust valves early. Engineers are now attempting to reclaim that lost percentage by abandoning the strict silos of the Otto and diesel cycles. The 37% wall is the result of a static engine architecture, a design locked into a single geometry that cannot adjust its internal state to counteract these thermal losses. Nicolaus Otto established the baseline for the modern gasoline engine in the late 1800s. His philosophy required the engine to draw in a homogeneous mixture of air and fuel, compress it, and wait for a timed electrical spark to initiate the power stroke. Rudolf Diesel pursued a more efficient, high-compression alternative. Diesel eliminated the spark plug and the premixed charge. His engine compresses pure air until it reaches extreme temperatures, only injecting fuel at the last possible millisecond to trigger ignition. These two competing methods of heat addition created a permanent rift in automotive design, forcing gasoline and diesel technology into separate evolutionary paths for over a century. To understand why these engines perform differently, we look at their PV diagrams, tracking internal pressure against cylinder volume. The Otto cycle relies on isochoric heat addition. When the spark fires, pressure spikes almost instantly while the piston is stationary. This rapid burst of energy allows the engine to rev quickly. However, the intensity of this pressure spike limits how much we can compress the fuel before triggering uncontrolled detonation. The diesel cycle uses isobaric heat addition. Fuel is injected as the piston moves down, meaning the pressure remains constant even as the volume inside the cylinder increases. Because the pressure stays high throughout a larger portion of the stroke, the fuel provides a sustained pushing force against the crankshaft. This duration of force is what generates high torque. The total area inside these curves represents the work done, but the delivery method defines the engine's character. The Otto cycle's instantaneous burst favors high-frequency RPMs, while the diesel cycle's sustained push results in the heavy pulling power of low-end torque. These thermodynamic behaviors are enforced by the fuel's molecular structure. Octane is a rating of stability. It measures a hydrocarbon's ability to resist breaking down under heat and pressure. Gasoline must remain chemically inert during the entire compression stroke, waiting for the spark to provide the necessary activation energy. These efficiency and torque profiles are inherent to the chemistry, meaning any attempt to bridge the two cycles requires a total overhaul of fuel delivery and mechanical geometry.
For most of the 20th century, diesel engines were limited by mechanical injection pumps tied to the crankshaft. At low speeds, fuel pressure was weak, leading to poor atomization and thick black exhaust smoke. Common rail technology decoupled injection from engine speed, a shift that entered the passenger car market in 1997 with the Alfa Romeo 156. By storing fuel in a shared high-pressure rail at 36,000 psi, the system allows the injectors to fire multiple times in a single millisecond. This gives the engine control unit total authority over the combustion event. An electronic diesel can now perform a pilot injection to preheat the cylinder, smoothing out the explosion and removing the characteristic diesel clatter. A post-injection then fires to burn off residual soot, helping the engine meet modern particulate standards that were once unreachable for compression ignition. This was the first true hybridization of the cycles. It allowed the diesel engine to adopt the smoothness and timing precision that was once the exclusive domain of gasoline. Gasoline engines faced their own geometric limitation, the fixed compression ratio. High compression maximizes fuel economy, but leads to knocking when a turbocharger adds boost. Lowering the ratio allows for boost, but makes the engine sluggish and inefficient when the turbo isn't active. The Infinity QX50 introduced the first production solution to this compromise, the variable compression turbo engine. Instead of a fixed connecting rod, this engine uses a complex multi-link system controlled by an electronic actuator. During highway cruising, the actuator pivots to raise the piston's reach, creating a high compression ratio for maximum thermal efficiency. Under hard acceleration, the actuator shifts to drop the piston's peak height. This lower compression ratio prevents knocking, allowing the turbocharger to safely force more air into the engine. By enabling the combustion chamber to physically reorganize its own volume, this system provides optimized cruising efficiency and high-load performance within the same engine block. The final convergence of these two legacy technologies is homogeneous charge compression ignition, or HCCI. Like a gasoline engine, it draws in a perfectly uniform mixture of air and fuel. But instead of waiting for a spark, it squeezes that gasoline mixture until the entire volume auto-ignites from pressure alone, mimicking a diesel's core operation. Because the fuel burns uniformly at a lower temperature, HCCI produces almost no nitrogen oxide or soot, reaching efficiency levels that were previously considered impossible for gasoline. The challenge is timing. Without a spark plug to trigger the event, the engine must precisely control the temperature of the air and the pressure of the cylinder to prevent a catastrophic mistimed detonation. Making this work depends on high-frequency feedback loops that process thousands of sensor data points every second. In modern HCCI, the combustion is managed by software as much as it is by metal. These advancements are all targeting that 37% thermodynamic wall established at the dawn of the automotive age. Common rail injection, variable geometry, and HCCI combustion act as a collective toolkit, reclaiming the 9% gap that separates real-world engines from their theoretical limit. Modern designs use piezoelectric injectors and variable-length linkages to adjust their own physical and chemical parameters in milliseconds. The boundary that once separated Otto's spark from diesel's pressure has effectively dissolved. Internal combustion has transitioned into a computationally driven thermodynamic system that adjusts its own physical and chemical states to capture every available joule of energy.